Thank you. So this is joint work with Vikraman Choudhury and Neel Krishnaswami. And in this talk, I'm going to try to convince you that type checking is really proof reductions in classical linear logic. So you might be thinking that you've implemented type checkers before, but don't remember thinking about linear logic. So the aim of my talk is to try and tell you that you really should be. And if time permits, I'll tell you a bit about the benefits of this perspective. So let's get started. We have a typing judgment, and we can see them as predicates, which takes three arguments, so context, term, and type. And how do we define such a predicate? Well, we have typing rules. So we can read these typing rules bottom up. So this says, to derive the predicate, which says lambda abstraction has type A arrow B, we're going to derive the predicate, which says E has type B in the extended context. So the colon dash I'm using here comes from the syntax of Prolog. And you also have function application. So the two predicates here correspond to the two premises on the left. So this is why we can see type systems as logic programs. And now, in order to do any type checking, we can simply write a query as a logic program. So this says, well, is it true that E has type A? And hope that our logic program will tell us true or false. So is our problem just solved? We can just do type checking by running a query. Unfortunately not. So let's think about subtyping for a sec. This says to derive that E has type B, we're going to derive E has type A, well, some A. We don't know what it is. We're going to have to guess it. And then say A is a subtype of B. So in order to resolve this goal, what would happen is we're going to match this predicate E has type A again and see actually, well, it matches with the same case again. And that's why it would go into an infinite loop. So this is why queries may never terminate. So we can't just expect to successfully do type checking this way. So the reason for this is the set of typing rules we could write is too unrestricted. And one way to put more restrictions is called bidirectional typing, which Nicola, I think, has kindly mentioned earlier before noon. So let's have a review of what this is. So given a normal typing system, we can transform it into a bidirectional one by now instead using two kinds of judgments, so two directions. And first one says we're going to check that E has type A, and second one says we're going to infer that E has type A. So we can, again, write our typing rules using our new judgments. So we're going to check lambda abstractions while inferring function applications. So the choice of whether to check or infer might seem arbitrary at first glance, but these are carefully crafted according to a series of criteria and recipes people have come up with over the years. So this example I'm using here comes from the Fenning recipe. If you're interested, you can read more about bidirectional typing in the recent survey paper by Jana Dunfield and Neel Krishnaswami. The most important criteria in crafting bidirectional type systems is called mode correctness. What does this mean? Well, the main difference from a normal type system is that now the judgments sort of have a direction to them. So instead of a relation, now there are partial functions. So check takes three arguments, so actually three inputs, context, term, and type. While infer takes context and term as input, and then give you a type as an output. So this is what I mean by mode, whether something is an input or an output. And saying the bidirectional type system is mode correct basically means that information flows nicely from inputs to outputs, and you sort of don't have to guess anything on the way. Let's actually have a look at an example. So this is a rule for function application. And to check that this rule is mode correct, we're going to start our starting information would be the inputs to the conclusion. So think of this again as running bottom up, and this is like your goal. So that's your starting information. And so if we know that gamma E1, E2, then we know the gamma in the left premise, and similarly E1. And by similar reasoning, we have gamma and E2 on the right premise. And now looking at the left premise, all the inputs are fulfilled. So by induction, we should be able to get the output of this premise, which would be A arrow B. And then we can grab this output and feed it in as an input to the right premise. So now all the premises are resolved. We can output B as the whole output of the system. And this is why this rule is mode correct. Let's think about if we've designed this rule differently. Say, for example, if we check all premises, what would happen? So again, our starting information would be the inputs to the conclusion. And then again, we have gamma and E1 and gamma and E2. Now this A sort of appears out of thin air. We don't know where it comes from. And this is why this rule is not mode correct. And the significance of mode correctness is really that you can see a bidirectional type system as a type checker if you read it bottom up and it tells you what you're going to do at each step, what are the other goals. And if a rule is not mode correct, you have to guess a type A, which is not ideal. So returning to our previous picture, so this is a bidirectional type system, and we can write the new judgments as predicates, so check and infer, and again writing our typing rules as logic programs. So as we've said before, we've annotated the modes here because it's very essential that all the rules are mode correct in order to read bidirectional type system as a type checker. So this is why we can see type checkers as moded logic programs. And returning to our subtyping example, now we can see it doesn't loop anymore because we've switched from check to infer. And people have come up with all sorts of extensions of bidirectional type systems over the years, and I'm just going to mention one here. So this is called strict bidirectional type checking by Adam Chapala and collaborators. And they're motivated by the fact that previously I could only check lambda abstractions, but actually sometimes we can infer them in order to reduce the annotation burden. So this expression here, suppose we know that increment has type int to int, we should be able to infer the type of this expression. So let's have a look at how to do that. So this would be in the extended context, increment x has some type. But we don't know what this question mark is. So let's go just one more step up. Great. So now looking at the right premise, we can sort of deduce from this that actually this question mark should be an int. And now we can propagate this information downwards and say, well, let's fill in this question mark is int, and then we can infer the type of lambda x inc x. So the thing to notice here is that this int is really an output of the system. So previously I said no matter we're checking or inferring, context is always an input. So here is a case where you have an output embedded in an input. And actually, in practice, you also have it the other way around. So input embedding in outputs, or like lots of layers of such things. And actually, in Scala, so due to Martin Odesky and collaborators, they color the type. So you can see whether each part of the type is an input or an output. As you can imagine, checking mode correctness becomes incredibly difficult in this setting, because our intuition about how information flows from inputs to outputs breaks down when we have, loads of layers of inputs and outputs. So we really need a better foundation for talking about fine-grained mode systems. So let's have a think about how we might come up with the foundation ourselves. So let's take a simple example. A type which takes list of A as input and output a B. And suppose this A is an output. So this is really just saying we're going to input a list of placeholders, which is going to be filled in with values later on. And this looks quite messy, so maybe let's treat input as default and label all the outputs. So we're just going to use some symbol to label the outputs, okay? And now instead of saying that this negation symbol labels the outputs, we can generalize this a little bit and say that this negation symbol switches the input-output notion of a type. Switches the input-output notion of a type. And that doesn't just restrict to atomic types. You could also switch the input-output notion of like multiple layers embedded type. And what do we want from this operation? Well, we want to say if we switch the input and output notion once, and then again, we should get the same thing. So there's really a sort of classical logic flavor here. And in addition, we want to say that we want some sort of computational interpretation to it, which we know pure classical logic is not great for. And that leads us naturally to classical linear logic, which happens to be a great setting to talk about such things. So let's look at a few inference rules. I'm using the sequence calculus presentation here. So we can think of the left-hand side as input and right-hand side as output. So this rule just says, well, if I get an A as input, I can just send it along and out as output. Second rule says, if we can output an A, well, we can input an A door. Again, remember, A door means switching the input-output notion of A. And we can also flip this the other way around. Here comes the important rule, which is called cut. So this says if we can output an A and output an A door, we can essentially make these two types communicate with each other. So like link them together in the sense that we are going to match with all the inputs in A with all the outputs in A door and vice versa, so that they sort of don't affect the environment anymore and they can go away. And there are also other typing rules for like and or, and their doors, which we'll omit for now. So to talk about computations, people have come up with all sorts of term calculus for classical linear logic over the years. And I'm just going to use one here. So if we label A and A door with terms, and we're going to record the fact that we're making T and T prime communicate and link them together. So this is really just sort of tell you how the information flows. And then a program just becomes a collection of such linkings. And again, just linking all the information together. And to do any sort of computation, what we need to do is actually make the information flow. Like this is a dynamic thing now. And that means maybe there are loads of linkings and I'm going to reduce them to like less linkings, or maybe a big linking could be separated into smaller ones. So computation actually corresponds to cut reductions in classical linear logic. So the language I'm using here is due to Reddy in a paper called The Type Foundation for Directional Logic Programming. Notice the mention of logic programming here. And this is especially inspired by Samson Abramsky's computational interpretations of linear logic. And as you've probably seen in other sessions, session types is another great setting to talk about such embedded mode information. And we've chose Reddy's language because it has a natural link to logic programming. So let's have a think about, actually let's look at an example of how we might write such a logic program. So a simple example, write a predicate called not, takes a Boolean as an input, output a Boolean. So the tensor product here is just the classical linear logic version of the AND type. We're gonna say, well, to derive that not A is B, we're gonna match A with a case pattern. If it's true, then B is false. And if it is false, then B is true. So again, remember that this link links opposite types together. So here it's really saying like if A has opposite type to T dual. T stands for true. So to run a query, we can say, okay, we're gonna input a true. What's the output? We're gonna use a variable here and hoping the program will tell us what it is. So this query would trigger a substitution into A and B. Okay, giving this. And now it's going to match with the first case pattern and say, okay, so this would be the output of our system and saying X should have the opposite type of false. Again, opposite means switching input-output. And now, as we've seen before, these linkings come from the cut rule. So each step is really a proof, it's like a proof in classical linear logic. And these reductions are proof reductions in classical linear logic. Great. Let's return to our big picture again. So bidirectional type systems, again, we can write these judgments as predicates, check and infer, using constructs from classical linear logic. And now, if these directional logic programs type check, remember we've combined mode with type. So type checking really says that, well, information flows nicely and that everything is mode correct. So therefore, the bidirectional type system would actually be an actual type checker. So this is why we can see type checkers as directional logic programs. And now to run such type checker or doing type checking, we're just going to run a query. And as we've seen before, that this would trigger a series of proof reductions in classical linear logic. Great. So what have we talked about so far? Oh, one more thing missing here. So here we can see that context should be a type in directional logic programming language, which Reddy's language doesn't currently have. So we need inductive types. And let's recall the syntax, the grammar for context. And so to incorporate the previous example of lambda x dot inc x, the Adam Chapala example, we are going to extend the grammar of context with this, saying this type could also be an output. And this context could actually be written as an inductive type using constructors from classical linear logic. So we've extended a Reddy-like language with inductive types and co-inductive types because of the duality and show that the semantics is what we want categorically. So now returning to the big picture, what have we talked about so far? Well, we've seen that type systems can be seen as logic programs. And type checkers, well, type checkers coming from bidirectional type systems, can be seen as directional logic programs. And actually doing type checking, running the type checkers, correspond to query evaluation, which turns out to be proof reductions in classical linear logic. So that completes the big picture of the talk. But you might be wondering, okay, fine. So type checking is proof reductions in classical linear logic. So what? Well, let's think about how you might write a type checker. So you're gonna write some typing rules on paper and check that they're mode correct, okay? And if they are mode correct, you can read these rules bottom up and get an implementation out straight away. Great. But suppose fine-grained modes are involved, which happens a lot in practice, then we're stuck. We essentially don't know how to do check mode correctness anymore. Our intuition breaks down about how information flows. So what we're going to do instead is, after writing the typing rules, we're going to write them as directional logic programs. So notice that this step here is really not much of a jump. It's really writing the same thing in a different syntax. And if these things type check as directional logic programs, again, because they combine mode with type. And recall the linking thing is like linking, you can only link opposite types. And if everything type checks, it means like every input is matched to an output. You can't make up something out of nowhere. Then the original type system would be mode correct. So we can see our work as using directional logic programming as a formal foundation for mode correctness, which is especially useful in the situations where our intuition breaks down. And secondly, well, by writing now one type checker for directional logic programming language, from then on, we can just write some typing rules on paper. If they type checks, great. Get implementation out of it straight away because they're mode correct. So we get implementations of lots of type checking algorithms for free. So this is why we think it might be helpful to think of type checking as proof reductions in classical linear logic. So that's the end of the talk. Thank you very much, and I will take some questions. Thanks. Let's do him. Hopefully.
Questions?
Oh, sorry, I don't think I can hear you.
Oh, thanks. That was a very nice talk, and I like the connection to linear logic. I'm just wondering if this would work if you wanted to do type inference besides type checking.
Yes, yes. So great question. Thank you very much. So as we've seen, let's do seamless. Okay, so because in logic programming, you can essentially replace an argument with a variable, and then when you write, it's going to give you like what this variable is. So in the not example we've seen. So if we want to do type inference now, we're just going to replace the variable for type with an x, and it will reduce to a normal form which says what x is.
Thank you.
If that's clear. Thank you.
I think in your abstract you also outlined unsolved problems or further steps that you want to research. Is that correct? Could you
Yes.
elaborate on that?
Thank you for the question. Yeah, of course. Yeah, and thank you for checking out our abstract. We wrote some, so we were looking into how to, essentially we were trying to figure out what Reddy's reductions are, and we were working on a polycategorical framework for it, which we were looking at like Highland-Truman envelope and how normalization actually corresponds to this polycategorical version of normalization, of Unay dilemma. But our future work is first, we've extended with inductive type, and the next thing to look at is binders. So suppose our original type system is system F or something more complicated. And to translate them into directional logic programs, we do need some way to talk about these binders. And we're planning to look more into abstract syntax and variable binding by Marcelo and collaborators, which would allow us to accommodate more expressive type systems in this framework.
Great. Okay, let's thank the speaker again.
Thank you very much.